Okay, so good evening, everyone. I hope I'm audible, right? And my screen is also, I hope, visible. If anyone, please confirm it will be better. Yeah. Okay. Thank you for confirming. Well done. So, so this is the no sound. Okay, so it's not audible, right? It's not audible. I think Papya is saying that it's not audible, but any other person, it's not audible to you. It's audible. So please, um, so you can join whoever is not audible. Okay, she's not able to order. She's not able to. Yeah, right. I hope there is no problem from my side. So screen is also visible. So okay. So let's begin. This is the second tutorial. Okay. So let's start it. Okay. So I will start with the definition of vector space, and then I'll directly go to the problem. So this is tutorial second tutorial, linear algebra. Today is 31st July. So till now, if you have any problem regarding the course content or the problem you faced in the assignment or any places, you can ask me. I'll try to solve. Or any problem in this course, or even if you are reading some books like Hoffman Kunz or anything, or any other book for the linear algebra, and you face any problem till now, whatever the content you reached, up to at least up to second week material. If there is any doubt, you can let me know. I will try to solve those problems, uh, and I also solve some other problem. So so if you have any problem, you can let me know. I will try to do those in the earliest. Otherwise, I will start something. But you can also stop me and ask me those problems if you have any. Okay. So I'll start with the definition of the vector space. So if you remember, in the last day we have, whoever is attended, if you remember, then last day we are trying to understand what are the binary operations. But not much we have done, but we have done many things in the binary operation. But the main target to the binary operation is the group structure. I know all of you maybe know, but still I'll just quickly try to say what is group. A group is a set is with a binary operation is let G be a set with a binary operation star, that can be addition, that can be multiplication, that can be any type of multiplication. Okay, and yeah. So any type of operation, binary operation, it has to be is said to be group, is said to be group if first of all it is closed. If it is closed, if it is closed under the binary operation addition, the star. That means if we take two element A and B from the G, and A star B has to be in G. So that is if A B belongs to G, then A star B also has to be coming from G. And this is the very least property that it should be satisfy. It should satisfy the closeness. Okay, that is the closed under the binary operation, and satisfies the following condition. Satisfies following conditions. Satisfies following. I'll not take much time. That is, first is that it is associative with respect to the binary operation. And second is that there exists an element E in G such that A star E is equals to E star A is equals to A. That is called the identity element. And third is that for every A in G, there exists and B belongs to G such that A star B is equals to B star A is equals to E. So if you take G is the group of all real numbers and the binary operation as the addition, then in that case this identity element is nothing but 0, and this inverse is like that. If you take an element A, the inverse is minus A. If we take the set of all real numbers, non-zero real numbers, and the binary operation as the multiplication, in that case this identity is nothing but 1, and this one is that if you take A and its inverse 1 by A. Then A B is called, then B is called inverse of A, then B is called inverse of A, and E is identity. E is called identity of this one. Okay. Now we have inverse depending on the operation. Inverse identity depends on operation. If we take real numbers with the binary operation as addition, in that case, the identity is 0 and the inverse is minus A. If we take the multiplication with non-zero real number and consider the binary operation as multiplication, in that case the identity is 1, and in that case uh, inverse is a reciprocal. That's what it is. Okay. Okay. So let me remind you, last day some of you said that my speaking speed is little fast. So if you feel so, you can let me know. I'll try to slow down it. Okay. So these are the group, but the main fact what we need here, a group that is G with an binary operation is said with a binary operation that satisfies above all condition is said to be abelian or commutative if A star B is equals to B star A for all A and B coming from G. This is called abelian group due to the great mathematician Abel, so that's why it is called abelian group. Okay, I will not go much in the group structure. Now I will come to the vector space. A vector space, let A be a field. I am not going to say what is field here. Field is some kind of ring, and ring is some kind of structure which has two type of operation, addition and multiplication, but it satisfies some condition with the distributive properties. All these things is there, and field is something where commutativity as well as inverse property with respect to the multiplication should hold. Let A be a field and V be a set, then V is said to be vector space over the field F, which I'll write sometimes vector space V over A. Over A. Okay, this is in short I will write. Sometimes if it satisfy, if there exists two operation, there exists two operation, there is two operation, binary operation, that is called addition. This is the symbolical addition, and some other one that is called scalar multiplication. What is scalar? Scalar is means the elements coming from the field F. Scalar multiplication satisfying the following property. Satisfying the what are the following properties? First property is that in some sense, first property is that A plus B plus C is equals to A plus B plus C. Second is that this is associativity of the with respect to addition. Second is that there exists an element 0. I will denote it 0 in V such that A plus 0 is equals to 0 plus A is equals to A for all A belongs to V. Third is that there exists an element B in V for every A in V, there exists an element B in V such that A plus B is equals to 0 is equals to B plus A, called the inverse. Note that this is the addition. This is not, if we take V just and set, that does not guarantee that what addition means. But if we take V is real number, this is easy to realize, right? So I'll suggest whoever is not able to, whoever is mixing things with the addition and whatever it is, so I'll suggest them to, for right now, okay, I think Puppet, still you can't hear me, right? Okay, so okay, I'll suggest that if we consider V as the set of all real numbers or the complex number, that would be better to understand for right now, and the operations are just usual addition
Sir?
and the scale.
Yeah.
So can you hear me?
Hello?
Yeah.
Yeah, sir.
Okay,
Right
so
now, my problem is solved. Thank you so
okay,
much. Thank
okay,
you. Yeah.
okay. So I'll suggest you to consider like real numbers or the something like tuples of real numbers, that is tuple and addition as point wise, component wise, something like that, to understand things clearly. I will give an example and to understand clearly. So these two operations satisfied, and the another operation is that it is the commutativity for all A and B coming from V. If you look at carefully, this all four properties says V with respect to addition is an abelian group, nothing else, which I said earlier. Okay. Another operation, so this is the operation should satisfy with respect to this plus structure, with respect to this plus structure, and there is another structure that is scalar multiplication, which we see how those scalar multiplication things also behaves. So another structure is that, and okay, I have said this is 4, this is 4, this is will be now 5. 5, what 5 says, that there exists an element 1, I mean 1 is in the, let 1 be the identity with respect to let 1 belongs to F be the multiplicative identity in the field. Multiplicative identity in the field. Okay. That will exist. There exists multiplication. With respect to that, there will exist an identity. So then the condition is that for any A in V, we should have A dot A. This is scalar multiplication I am defining right now. There one can define a scalar multiplication, but that scalar multiplication have to satisfy some condition. This is what it is I am saying. What condition they should satisfy? You can define a scalar multiplication, but whether that scalar multiplication is going to satisfy some condition or not, you have to verify that, and that's what I am trying to verify. For all A belongs to V, we have to satisfy this condition, and for any C1, C2 coming from F, this is the sixth condition, we should have C1, C2, this is the usual multiplication in the field, and this is the scalar multiplication in the vector space where I am defining. That will be C1 dot C2 dot A. This is the scalar multiplication, and this multiplication here it is. It is just multiplication in the field. There is a many operation. We have a field, there exists a multiplication addition. Okay, but we have right now we have a vector space, we have a set, and we are defining two operations. We already defined two operations, but those two operations should satisfy some condition. That's what I'm explaining. What are the conditions they should satisfy? Okay. Another fact is that that for any C in the field and A B, okay, it's better to, okay, I think it's better to take some separate alpha beta in V. C of alpha plus beta is equals to C alpha plus C beta. Note that here it is scalar multiplication, here it is scalar multiplication, here it is scalar multiplication, here it is the binary operation addition. And eighth condition is that C1 plus C2 whole with alpha is equals to C1 dot alpha plus C2 dot alpha for all C1 belongs to C1, C2 belongs to the field, and alpha coming from the vector space V. So you have to be very careful from where the elements are coming. Okay. So then we say vector space. Okay. So what we have seen, we have defined two structure on the set V. One is addition, with respect to which this will form an abelian group, and on another is this is up to this is the abelian group. Another is then scalar multiplication that should satisfy some two basic property. This one and these all three property are some property which you can say the compatibility. We have two structure, addition and scalar multiplication. We need the complete compatibility, that is this. This is the distributive property. We need that distributive property, that whenever the things are getting as mixed, what the behavior looks like. Okay, so let's give an example. Let R be the set of all real numbers. Set of all real numbers. And let n be a positive integer. We know if it is a set of real numbers, then R is a field. R is a field with multiplicative identity. R with the non-zero actually, multiplicative identity 1. Okay. Now let's take R to the power n, that is a tuple of elements like A1, A2, An, such that AI is coming from the field R. Okay, and n is fixed. This is the set. Now define two operation on Rn. How? This is point component wise. That is A1, A2, An. If we take one element and another element is like B1, B2, Bn, then this will be component wise. Note that here A1, A2, An, this is one element coming from Rn, and B1, B2, Bn, this is another element coming from Rn. We have take the addition and defined the addition like this way, just component wise. I have defined this way. It seems very obvious, but be careful. We have to define something like that. We can't say anything. What I mean, this is obvious. So I can, if you are confusing with the things, like you can assume that okay, they are usually like this way. Later you can realize okay, they can be very different way also. I'll come up with some examples where this type of addition may arise surprisingly very different way. Okay, this is the addition I have defined, and I have defined a scalar multiplication. And scalar multiplication is, what is this? Scalar multiplication is the field from the set V to V. This is the operation. Okay, that is sending some element C and alpha going to the C dot alpha. So here if we take, let F is equals to R, real number. I am taking real number as the field, and V is equals to R to the power n. So how the multiplication, scalar multiplication defines? Let's take C coming from the field R, and A1, A2, An, this is coming from the vector space V, which is actually Rn. What I am to define as a vector space. Then C dot A1, A2, An, this is I will define as, this is the definition sign. These two is called definition sign. Okay. CA1 all the way CAN. Okay. This is the definition. So one can check Rn is a vector space over the field F. F is equals to R. So you can check. Most importantly is the distributive property, identity, all these things. So you can check these two property, especially this will also hold. You can guess very easily that that here if you just use these two property, this will hold. Okay, this is a vector space. Now we'll come up with a subspace. What is subspace? Let V be a vector space over a field F. Let V be a vector space over a field F. That means that satisfying all the property. V has two operation with one addition, one scalar multiplication. Scalar multiplication means multiplication by elements from the field F. Okay, and it satisfies some properties and which I mentioned there. Let W be a subset of V. Subset be a subset of V. Then W is said to be subspace of V if W itself satisfies itself is a vector space. W itself is a vector space over F. Okay, that means it has to first satisfy the closeness property. Okay, so what is mean by this? We have a vector space. That means we have a set V, two operation, one is plus and one is scalar multiplication. We should not write this way, but okay. And it is a vector space over F that satisfies some property which I listed above. Now, W is a subset. If I take W as a subset, what I am saying, W with respect to all the same operation, it has to be is a vector space over F. Then we say W is a subspace of V. If it's that means we have to keep all the operations same, addition and scalar multiplication, which is already here in the case of V. We will keep all those operation here is also as it is, but so we will define those two operations as it is on W, and we have to say that so that W itself is a vector subspace over it. But there is a point. Suppose I have taken W as a subset, and let's take two element A, B coming from W. Then A plus B, then A, B always coming from the space V. Now, as V is a vector space, then their addition is there, right? But who gives you the guarantee that this addition also be here? This it gives you the guarantee. For example, if we take addition, we have to define something different, right? So that it is does not satisfy something. If we take I mean that not necessarily hold. I have to show some example where this not necessarily hold. Okay, so let me give you one example. Yeah, I will come up with an example actually that its closeness is not there. Okay, I'll come up with an example. Okay, so but so there is no guarantee that this should hold. First of all, this is the condition, right? There is no guarantee that this should hold. Another point is that if we take some scalar C coming from the field F, we know that as A is coming from W, that is also will be in coming from V, and then C dot A that has to be element in the V. But who gives you the guarantee that C dot A has to be in W? If these two things does not hold naturally, then one can't say anything about the vector space, anything about the subspace, whether W is subspace or not. So, but interestingly, there is a very famous and very easy theorem. I will not prove, and that I hope discussed in class. That theorem that let V be a vector space over F, over a field F. Let W be a subset W be a subset of V, then W is a subspace of V if it satisfies following condition. I'm writing one condition, that is C alpha plus beta is in W for all alpha beta coming from W and C coming from F. So what it is says, look at very carefully. These two condition is also included here. How? If you take field, if it is field, so if you take C is 1, this should satisfy for all alpha beta belongs to W and C coming from F. So let's take alpha beta coming from W and C is 1. If this property hold, it is guaranteeing that alpha plus beta is in W. Okay. I have to take the guarantee this one. Let's take C is coming from the field F and alpha is coming from the vector space V, the W. Alpha is coming from the subset W. And let's take beta is 0. This property says that C alpha has to satisfy in W in order W to become a subspace. Okay. So these two condition is also there. Very carefully, these two conditions is also there. And interestingly, this condition itself is enough to show that W satisfy all the property. If it satisfies this condition for all alpha beta belongs to W and C coming from F, W will satisfy all those property I have listed above for the vector space. So this is what it is checked. One interesting fact I will share here, that if you consider this should satisfy for all alpha beta. So if you choose alpha is equals to 0, sorry, alpha need not be 0, right? Okay, let's take, let alpha is in coming from W is non-zero. Of course, W has to be non-zero. W is non-empty. So here I have to be careful. Let W be a subset of non-empty. Of I need non-emptiness always. I can't say without. There should exist at least one element. So as 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 W is non-empty, so let's take one element is there. One element will be there, and this should satisfy, right? So if this satisfy, let's choose C equals to -1. Then what it says, minus of alpha plus alpha. I have chose beta is equals to alpha, and alpha is there, and I have choose beta is equals to alpha. Then we have this property. This should satisfy in W. But what is this? This is 0. So that means it is necessary that 0 is in W in order W to become a subspace of V. So that means a subset will be subspace if necessarily the 0 of the vector space, the mother vector space V, there exists a 0, right? Because that is a abelian group with respect to the addition. So with respect to that abelian group, you will have an element. So what you have to, that 0 has to be there. So this is the very basic check. I will also use this fact to show some example where you can easily discard whether whether a subspace is a vector space or not. So, okay, so let's let's go to some example. So this is something interesting theorem. Okay, whoever is a very new in the mathematics in after 12, for them from now onwards you will see theorems, lemma, corollary, examples, but not like integration derivatives. They are there. Those things are there, but not directly visible as even in the 12 level. Okay. So let's come with an example. Okay, till now whatever I have discussed, is those things very clear to you? If it is not clear, you can let me know. I'll try to explain things in more easiest way. Is it clear? You can feel free to ask me if you don't feel somewhere is not audible or not clear to you. Even those things are seems very trivial. Okay, so this is one of the questions, and here I hope I'll get whatever I have discussed, those type of things. So what it says, for real number AB belongs to R, the straight line LAB is collection of all those xy such that ax plus by is equals to 0. Okay, are subspaces. of the R vector space of R2. So let's take LAB set. We can think it as a set. So what is that? The collection of all xy belongs to R square such that AX plus BY is equals to 0. So this is of course subset of R square. So as we have said there, R to the power n is a subspace, is a vector space over the field R. So we observed, in fact, here I can point out, in fact, similarly here I have pointed out that R to the power n is a vector space over the field F equals to R. Similarly, C to the power n, C is the space of all complex number, is a vector space over the field C. So now the question here, from here we can think whether R to the power n is a vector space over the field complex number, whether C to the power n is a vector space over the field real number with respect to the usual pointwise multiplication, pointwise addition and the scalar multiplication, whatever the addition and scalar multiplication I have defined. The coordinate wise addition and scalar multiplication is just the component wise multiplication. So with that, whether R to the power n is become a vector space over the space over the field real number, over the field complex number, whether C to the power n is a vector space over the field real number, you can check. So there will be some problem, you can check there. Okay. So this is a vector space. We observe that R square is a vector space over the field R, and this LAB is a subset. So if you look at very carefully, here 0, 0 is there. Okay. If you replace x and y 0, this is satisfied. So that means 0, 0 is in this set. So you can't discard very easily. But okay, as you can't discard, so let's try to prove by using the theorem which we have mentioned here, that a subset will be vector space, non-empty subset will be vector space whenever it satisfies this condition, that C alpha plus beta belongs to W for all alpha beta coming from the set W and C coming from the field F. Okay. So as 0, 0, clearly 0, 0 point is in LAB. That says LAB is non-empty, right? Let's take alpha beta, two element coming from, so alpha beta two elements. So let's take alpha is equals to A1 comma B1 and beta is equals to A2 comma B2, two element coming from the set LAB, and C is coming from the field R. That is what it is, right? Here it is, this is the field. Okay. Then C alpha plus beta, let's check what it is. Here it is usual pointwise multiplication, coordinate wise multiplication, addition. Here it is coordinate wise addition, and this is the scalar multiplication, component wise scalar multiplication. That means C with A1 comma B1 plus A2 comma B2. This said CA1 plus A2 comma CB1 plus B2. But note that as these two elements are in LAB, they should satisfy the basic condition what is needed to become an element in LAB, that is this one, and this should satisfy the condition A2x plus B2y is equals to 0. Now this will be an element in LAB if it satisfies the condition. What is the condition? That C A1 plus A2 whole x plus C B1 plus B2 whole y, that is equal to 0. We have to check whether this is satisfying or not. So let's check whether this is satisfying or not. We can write CA1x plus A2x plus CB1y plus B2y. So this can be written CA1x plus B1y, because we know the addition is associative, we can take addition interchange. Okay. And A2x plus B2y. But look at carefully, we already know this 2 is 0. So this is 0 and this is 0. So that means this is C into 0 plus 0, that turns out to be 0. So that means this element CA1 plus A2 comma CB1 plus B2, this element is sitting inside the set LAB. And this says, by that theorem, this LAB is a subspace of R2. Is this problem clear to all of you, or any doubt? Because these are the easiest problem. I will suggest, in fact, you should try to this easiest problem if you are not able to solve any critical problem. Because if you are not able to solve critical problem, you should try to solve the easiest problem. And after that, you can try something else. Okay. So if you have any still, if any one of you have any doubt anywhere, you can ask me. I'll try to explain. Because at least you should learn at least you should learn something before going to, because if you're not able to understand these things right now, so after a few weeks later there will be difficulty, so it's better to try to understand things right now. Okay. So okay, what are the second question was, this is the first questions, and the second question was that LABC is given by this way: ax plus by is equals to c with c not equals to 0. The straight line are not a subspace of real vector space. So question was let C belongs to real number and C is not equals to 0, and L A B C, this is equals to all those A B C, I think, all those XY, not sorry, all those XY, yeah, why, how A B C can be XY coming from real number such that AX plus BY is equals to C. This is also subset of R square. But here comes the point. Question whether LABC is a subspace or not. Is a subspace of R2 or not? This is the question. Okay. Whether LABC is a subspace of R2 or not. So anyone can say whether it is subspace or not. Whatever we have discussed till now on the basis of that, or the class, whatever discussed in class. Here, one condition is there important, and C is not equals to 0. Because if C equals to 0, we have checked that's a subspace, right? That we have checked before. That if C is equals to 0, that's a subspace. But if I take C is not equals to 0, whether this is a subspace or not. This is not difficult. You can try little. You can, if you are listening carefully, so you can try little. Whatever the condition, basic condition, I have said that you have to, a subset is subspace or not, you have to first hit with a very basic necessity to become a subspace. What is the one of the basic necessity I have said? General condition is that alpha, for any alpha and beta coming from L, A, B, C, and some scalar like P coming from the field, or F coming from the field. This is the basic necessity, that this is the general condition, that F alpha plus beta has to be in L, A, B, C again. But apart from that, I have said another thing, that necessity. Here I have said one thing, if you look at carefully, that if it is subset, then 0 has to be there always. 0 has to be there always if it is subspace. Of course, here it is maybe non-empty, because you can always get a solution of this fact. Whether LABC non-empty or not. Question is whether LABC is non-empty or not. The question is yes, if A is not equal to 0, because you can check, you can find X and Y accordingly. Like if you take X equals to 0, then what will be Y? Y is equals to C by B. Yeah, you need B has to be non-zero. Then in that case, it will have the solution. Otherwise, you will not get the solution. Okay. Take B not equals to 0. So that means there is some point always. So LABC is non-empty. If we take A or B, at least one of them is non-zero. Okay. So whether it is subspace or not, I think I'm not asking a very difficult question. Is it subspace or not? Any guess? Okay, huge long silence. Whether 0, 0 is there or not. 0, 0 is there. This point 0, comma 0 belongs to R2 is the zero element of the vector space R2 over R. So question is whether not a subspace of R2, that's true. Whether this is belongs to L, A, B, C under the condition C is not equals to 0. Zero element has to be there. Okay, as I have said, it is not a subspace of R2. That's of course true. But the reason is that you may find many reasons, but this is I believe one of the simplest reason. No, you can check that 0, 0 is not there. Just replace 0, 0 here. This is not equals to C because C is non-zero. So what we can understand here, whenever you are giving to check whether a subset is subspace or not, you just first hit with the 0, whether 0, 0 is there or not. If 0, 0 is there, then we can check the generally. If 0, 0 is not there, you are clear that it's not a subspace. Okay, is it clear? I expected that at least this answer will be from some of you. But okay, it's not a problem. Okay, so let me check one little difficult subspace problem. Not much difficult, but yeah, this one. I hope screen is visible and the question I'm writing here, that is also I hope visible. This is the question. So let's take u is equals to xy belongs to R2 such that x square satisfying the condition 4xy minus 4y square. This is a subset of R square. So question is whether u is a subspace of R2 or not. Whenever there is a, you can clearly check 0, 0 is there in this situation. Okay, because if you replace 0, 0, ultimately both side will be 0, 0. So 0, 0 is there. So 0, 0 check is not going to give you the counter here. So whether it is becoming a subspace or not, that's the point. The answer is no, but you can create example by guess. But let me give you the very standard way, but you should not try to that standard way because that is time consuming and that's not very, time is for this type of problem, you don't take much time. So for example, if you take x equals to 0, I'm just giving you x equals to 0, and so what will happen? You will get that 4y square is equals to 0. Oh, sorry, 0, 0 is there. So if you take x equals to 1, let's take x equals to 1, x is equals to 1, then what will be y? 1, that means it should satisfy the condition 4y square is equals to this one. So this will be like 4y square minus 4y plus 1 is equals to 0, right? So that means 2y minus 1 whole square is equals to 0. That will give y equals to half. So that means 1 comma half, this term is in R2, right? Similarly, if you take y is equals to 1, what will happen? You will get x square equals to 4y minus 4. That will be like x square minus 4y plus 4 is equals to 0, right? So this will give x minus 2 whole square is equals to 0. That will give x equals to 2. That means this is not R2. This is an R2, but this is also in U. That means x is equals to 2 and y is equals to 1. That is in U. So if it is subspace, then their addition has to be there. What is that? This is equals to 1 comma half plus 2 comma 1. So this is equals to 3 comma 3 by 2. So let's check whether this is there or not. This is x and y. So 3 square is equals to 9. We have to check that x square is equals to 4xy minus 4y square. So what is this right hand side terms becomes? Right hand side terms becomes 4 into x is 3 and y is 3 by 2 minus 4 into y square 9 by 4, right? So 4 will cancel out. This will be 2 and this will be like 3, 3, 9 to 18. 18 minus 9, this is 9. Oh, this is happening. Just this is happening. So to take some other case. Okay, so let's take 2 here and 1 here. How this will come? Okay, let me 2 here, 2 plus I'm coming to how the 2 plus 2 comma 1 plus this is 2. This is what it is I'm taking. 2 times plus 2 4. So this will change to 4 into 2. So in that case x is 4. So x square 4 square is equals to 16. So if we calculate the right hand side, so what will be, let's I hope it's not becoming 4 16 again. So 4 into x is 4, y is 2 minus 4 into 4. I'm writing correctly. X is 4, y is 2. Yes. 4, 4, 2. Okay. It's becoming again between. Okay. Again it is becoming. This is becoming 16, so it's matching actually. So those two terms also be there. Okay, so let's go. If xy is coming from the set what is u, that should satisfy the condition that x square is equals to 4xy minus 4y square. That says 4y square or plus x square plus 4x minus 4xy is equals to 0. That says x minus 2y whole square is equals to 0. That means either x is equals to 2y or x is equals to, no, always x equals to 2y. That's what it is. This is the condition. So this is the condition. Those terms will be there, right? Oh, this is the term. So that is if xy or if or not xy will be in u if and only if x is equals to 2y. 0 0 is there. 0 0 is there. Point is that it is subspace. I am trying to prove other way. It is subspace. Why it is subspace? Xy will be there if it satisfies this condition. But if it satisfies this condition, if and only if x is equals to 2y, right? So these are the, I mean, these are the useless things then right now. These are the useless things. From here you can start. That if xy belongs to there, that will satisfy this condition, and that will be say that you can check here, and this will happen that x equals to 2y and x equals to 2y. So now if you take two element x1 and y1, which is coming from u, and x2 comma y2, that is coming from u, that satisfying necessarily that x1 is equals to 2y1 and x2 is equals to 2y2. Right now if you take x1 plus x1 comma y1 plus or some scalar multiple c times x2 comma y2, this is what it is I have to check, right? C is coming from, let C is coming from the field F, and these are the two arbitrary elements I have taken, and then I will have that Cx1 plus x2 comma Cy1 plus y2. Now let's check whether 2x1 2 of Cy1 plus y2, which is equals to 2c times y1 plus 2y2, which is equals to c of x2 plus sorry, x1 plus 2y1 is x1. So x1 plus 2y2 is x2. So this is what it is satisfying. So that means cx1 plus x2, comma cy1 plus y2, this term is in U. So that says U is a subspace of R2, and you can check the other one. This is subspace. This is maybe not the subspace of R2, not the subspace of R2, because this happens if and only if similarly x is equals to plus minus 2y. So x is equals to 2y, for that it happens for all x equals to 2y, or x is equals to minus 2y, in that case also it happens. But if we take two element like x is equals to, let's take y equals to 0, not 0 I can't take, so y equals to 1, so it will be like 2 comma 1 is there and minus 2 comma 1 is there, right? This I am just giving the short hint, or you can say sort summary, why this one is not a subspace. You can check 2 1 and minus 2 comma 1, this is in U dash, but if you add them, what will have, you will have 0 comma 2, but 0 comma 2 is not here. You can check, if you replace x equals to 0, y equals to 2, that's not becoming 0. Okay, so that's why it is not a subspace. Okay, that's okay. Let me write, let U dash is equals to all those xy coming from R such that x square minus 4y square is equals to 0. Then clearly x is equals to plus minus 2y. So that is 2 comma 1 and minus 2 comma 1 all are in U dash. But minus 2 comma 1 plus minus 2 comma 1, which is turns out to be 0 comma 2, that not belongs to U dash. So U dash is not a subspace of R2. Is it clear to everyone? Sorry that I have initially I have mixed with the fact that maybe initially was not the subspace. Okay, so let me go to the this main problem which are supposed to solve. Yeah, here it is. So these are little difficult, but not much. Okay. Uh, okay, if you have any problem till now, even those are very simple and very basic, or from the previous tutorial what I have discussed, or any other questions, you can ask me. I'm supposed to solve those problems. So this is the biggest problem I think on the assignment which I should discuss. I mean, which are not supposed to submit. Okay, these are not blue colored exercise, so I hope screen is visible and clearly visible this problem. So what it says, let's K be a field, and whoever is little difficult to understand what is field, you can consider K is real number or complex number. It's better to understand complex number, or real number is also okay, I believe, for here. And let Kx be the set of all polynomials with coefficient in K. So what is Kx? All polynomials, something like ai x to the power I equals to 0 to n, such that n is any positive integer, and ai are coming from the field K. So these are the polynomials over the field K. That's what it is called. If you take the real R, so this will be the space of all polynomials over the field real numbers. Okay. So that's real coefficient polynomials. So this is what it is Kx. Let epsilon is a map which sends every element in fx to kk by the evolution map. What this says, epsilon is the map that maps every element to this is kk. What is kk? That is the collection of all functions from all k valued function from k. Okay, this is what it is mean. But this is also power set. If you take finite set, this this will be considered as the power set. Okay. Okay, so I think someone asked something. So x minus 2y, x plus 2y equals to, therefore either x equals to 2y or x equals to minus 2y. So u dash is equals to union of, yes, that's true. That's true. And if you take two elements from here and there, if you look at carefully, if you just consider the first set, that 2t comma t, that itself is a vector space. If you take another set, that minus 2t comma t, that itself is a vector space. But their union is not becoming a vector space. Yeah, one very interesting point is pointed out by Lolit. So let's before going to this, so let me just quickly. So here, okay, let me erase this and okay, I think I can do something else. Use that one. Okay. So what this point is pointed out, that's good point. Actually, though this is one of the theorem. Actually will be help. It will appear or you have encountered many places. So that is that. Look at very carefully. Look at very carefully. If you take u1 is equals to all those x and y, such that x is equals to 2y, of course coming from real number, and u2 that is equals to x and y coming from real number, such that x is equals to minus 2y, are individually subspace of R2, right? They are individual because we have checked previously that this type of things is a subspace. Okay, that's what it is actually turns out to be, that x square is equals to 4xy minus y is 4y square, something like that. Okay, that's same thing. Okay, so this is what it is, a subspace, individually subspace, but their union u, which is equals to union union u2, is not a, so better to write this is v1 to symbolize things v2. So this will be v1, this is v2, this is union set. v1 v2 is not a subspace of R2. So what you obtain from here, if you take two subspace, their union need not be a subspace. So thus union of two subspace need not be a subspace of V. I mean main subspace. So from here, one can ask, okay, so what we obtained, that if you take two subspace of a vector space, common vector space of course, their union is not becoming a subspace. Okay, that's fair enough. You have the counter example here. So now the question is that, simple questions I will not discuss, that if whether the intersection of two subspace is again a subspace or not, whether the intersection of two subspace, of course we are on the same vector space and two subspace are of the coming from the same vector space. Okay, two subspace is again a subspace or not, whether the intersection of two subspace is again a subspace or not. So you can check. This is interesting question. Thanks to Loli. And answer is yes. You can check. That's okay. So let me go back to the problem where I was there. So k power k means this is the set of all functions which k valued functions from the set k. Actually, if you take a and b to set, what is mean by ab? That means all the function f from b to a. If I am not wrong, b to a. I hope. Just a minute. To the power n, yeah, this is correct, absolutely correct. All the functions a valued function from b to a, this is what it is. For example, let me give you very, so if you take infinite set, this is what it is. But interestingly, if you take two set a and b, they are finite set, so this is means the power set. Okay, power set means collection of I mean, okay, let me. So this is what is power set type of things. I mean, if you take B is the two coordinate set, then this will be the power set. Okay, now point is that if you take R and this is n, instead of n, if you consider this is as 1 to n as a set with n elements, then what is mean? This means all the tuples we know, but if you consider n as the set with n elements like 1 to n, in that case, this will be each sequence or each tuple, not sequence, each tuple, each function from the set 1 to n to the real number, right? What is that? That f of I is equals to, uh, if I take a is an element, a1, a2, an, then this can be correspond with a function fa. That sense, f of I is equals to a. Very interesting, now that r to the power n, which I mean that tuple of integers, tuple of real numbers, n tuple of real numbers that can be think as a set of functions on the set 1 to n with real value. Okay, so this is what it is valued. Okay, I am not going to much here. If it is clear to anyone, you can understand things what it is. If it is not clear to this fact, you can forget. Okay, that's not very necessary right now. Okay, so what it says that epsilon is sending every element to something. What it is? So it is already given how it is epsilon sending a element f is coming from here, let f is coming from kx, then epsilon f that is in kk, that means epsilon f is a function from k to k. What is how it is defined? Epsilon f, if you take an element coming from k, that will be f of a. Okay, note that f is a polynomial in kx. F is a function in kx, that means it is a polynomial. So if we polynomial with the coefficient coming from k. So now if we here ai's are coming from k, if we replace elements by k, elements of k by x here, I mean if we replace x by the elements of k, we will get the ultimately this will become an element of k. So that's why it is well defined. Everything is there. So let's come back to the question. So what is the question? That this is injective if and only k is not finite. So what is the injective here? Question is what is mean by epsilon is injective. So it is clear how these things I mean here, because this is definition. Because on the basis of definition, you have to solve the problem. So stick to the definition. The definition is clear to you. So there, epsilon is just sending every element to some function. What is that function? That function is called evolution function. That function at the point A is gives the value f at A. Okay. So injective means if for some f coming from kx, that is a polynomial, and if ef equals to 0, then we should have af is equals to identically 0. So what is mean by af 0? It is mean by af at the point a is equals to 0 for all a belongs to k. And what is mean by this f equals to 0? This means f of b is equals to 0 for all b belongs to k, right? So question is, excellent. If for all f belongs to epsilon f is 0, that means this one. That says very, oh no, yeah, okay. So what you obtained f b is equals to 0, but I have not said the function is for all b belongs to k. Here what is f? Remember, f is a polynomial. So here I have missed something else. Okay, so here I have missed very super thing. Okay, sharing the mistake I made. So what is mean by this? What is mean by this? Remember, if is a polynomial over the field A. That is, if f is equal to summation of ai x to the power I, let's write it as b for all b belongs to k, f is equals to this is polynomial just, okay? So what is mean by f of b? That means summation of ai b to the power I, that is equals to 0. This is what it is I have given. For whatever b you choose, this is equals to 0. For all, no. So we say f is equals to 0 sorry, we say f is equals to 0 if all ai's are 0. No, that is 0. If f of p is equals to 0 for, one second. What I have to choose? I have to choose this is 0. This is just as a function 0. This is a function 0. This means that f of whatever the element I am coming from, this is a polynomial 0. That means we say if all ai equals to 0, that means f is equals to 0 dot x 0 dot 1 plus 0 dot x to the power 1 plus 0 dot x to the power 2 plus all the way plus 0 dot x to the power n, something like that. So that means all the coefficients are 0. That's what it is I mean. Okay, I hope this is clear. This definition is clear. If 0 means, let's take set of all polynomials, okay? So what is mean by the 0 element here? Okay, why the 0 element is look like this way? When you are taking the set of all polynomials, this is the kx, and here the elements are look like a naught x plus a naught, sorry, it looks elements are a naught plus a1 x plus a2 x square plus all the way plus a n x to the power n, and another element is like that a dash a1 dash x plus a2 dash x square plus all the way a n dash x to the power n, okay? So now if we add them by component wise, like a naught plus a1 plus a1 plus a1 dash, this is the addition, and scalar multiplication is just scalar multiplication. That way it will become a vector space. And here the 0 element is nothing but the 0 element is nothing but the 0, all 0. That means 0 dot 1 plus 0 dot x plus, this is what it is 0 element. Okay, so this is what it is I mean the 0 element. Okay, so let's come back to the main question, that's the injectivity. If AF is equals to 0, you have to prove that injectivity means if for some F belongs to this, EF is equals to 0, then you have to prove that F equals to 0, right? So what is the question says? Question says this is injective if and only the set field K is not finite. This has to be infinite, okay? So the proof, so what I am trying to prove? I am trying to prove that epsilon from the field Kx to K to the power K is injective if and only K is not finite, okay? So let me check how this is happening. If epsilon is injective, then epsilon f equals to 0 implies that f is a zero, f is the zero element in kx. If so, we know this, or this is the fact. This is fact we have. The point is that we have to prove k is finite. Okay. If this is equivalent. Okay, so this is equivalent. This fact is equivalent that if EF is equals to EG, that is implies that F equals to G. This is also injectivity, right? So I will prove this one, not this one. Okay. So equivalent, you can say this is equivalent. AF equals to G. This one is for any F G coming from the field K. It's okay. This is what it is. So let me change the statement then. I mean, this fact is also equivalent to this fact, but I will prove this one. If for some f and g coming from this, epsilon f equals to epsilon g, then as a function they has to be equal. This is what it is, the essence things. Okay. So now let f and g both are polynomial of degree n. Let f and g both are polynomial of degree n1, n2. Okay, are polynomial of degree n1, n2 respectively. I have taken two polynomial, and for which we know EF is equals to EG. Okay. Now we have to prove that k is finite. If k is not finite, okay, let I'm going to why k is not finite. Then f minus g, this is a polynomial, and let without loss of nullity, that's n1 and n2. These two are the integer, right? They are polynomial degree. So that means either n1 is strictly less than n2, n1 is less than equals to n2, or n2 equals to less than equals to n1. So if n1 equals to n2, then we can choose the common one. If not one, which one is the maximum, we'll choose. Let without loss of generality, n1 is greater than equals to n2. If n2 is greater than equals to n1, then we will choose the n1. So then f minus g is a polynomial of degree n1, but this is says that e of f minus g is equals to 0, right? That means f minus g at the point b is equals to 0 for all k b coming from the k. Now by the fundamental theorem of the algebra, this is says what is the, I think the statement says, yeah, the identity theorem of the polynomial. That's what it is, the fundamental theorem. One second. Okay, for all b belongs to g, but if f is a polynomial, it can have polynomial of degree n, then it can have maximum n number of 0, right? But we know if p is a polynomial, whatever the field doesn't matter, polynomial of degree n, then it can have maximum n number of distinct polynomial. But if k is infinite, but here if k is infinite, then f minus g have infinite number of distinct root. This is 0. A polynomial of degree n have at most n number of polynomial of degree n can have at most n number of 0. This is what it is. So f minus g have infinite number of distinct 0. And that happens, then it can happen only when f minus g actually the 0 polynomial, that all the coefficients are 0. That says f equals to g. So let me go through once again. So what we have to prove, that epsilon is injective. I have said one side only. Epsilon is injective, then k is finite. That is what I am trying to prove. So it is injective means what I can say, if for any f and g, if we have ef equals to eg, then we have to prove that f equals to g. That's the injectivity. So if I consider f and g both are polynomial and of degree n1, n2, without loss of generality I am taking n1 is greater than equals to n2, then f minus g, it is again a polynomial of degree n1. But by this fact we can say that e of f minus g is 0, right? That means f minus g at b equals to 0 for all b belongs to k. We have assumed injectivity right now. Okay, now we know that if you have a polynomial of degree n, whatever the field doesn't matter, it can have maximum n number of distinct root. Okay, and that gives the identity theorem that if you but here what it says, that f minus g, that is a polynomial of degree n1, maximum of degree n1, that have infinite number of roots or zeros. But that can only happen when the polynomial itself is a 0 polynomial, that all the entries are 0. So that's all the coefficients are 0. That means f equals to 0. So that says that is a contradiction. So k is finite. On the other hand, if k is finite, I have to prove that, then we need to prove that, sorry, k is inf k is k is infinite. On the other hand, if k is finite, then we can say that it is not injective. Okay, we need to prove that what was the question? This is the prove that epsilon is not injective. This is what it is I have to prove. That will settle the things. So if k is finite, let a1, a2, an are only distinct element in k, then consider the polynomial x minus t1, x minus t2, x minus tn. This is a degree n polynomial, and p of t is equals to 0, p of b is equals to 0 for all b coming from the field k. Okay, but p as a polynomial, so what this means, this is epsilon of p is equals to 0, but p as a polynomial is not a 0 polynomial. So that says p P is not equal to 0, that says epsilon is not injective. Is it clear? So what we first proved? We have to prove that epsilon is injective if and only k is infinite. First we have said if epsilon is injective, then we have proved that k is infinite. It cannot be finite. On the other hand, I have to prove if k is infinite, then epsilon is injective. But that's didn't I prove the same thing? One side is clear that if k is what we first proved, we have started with the fact that epsilon is injective. Then we claim that k is infinite, and we settled. Yeah. Sorry. I think I have made little mess. Let me go through once again. Injective if and only. Yeah. Acha. Now I got it. K is not finite. Yeah, that's correct. K is not finite. This is what it is. So let's start with f and epsilon is injective. Then f and g two polynomial. We have f minus g is once again a polynomial. If epsilon is injective, then f minus g is identically 0. Now, if k is finite, identically 0, the polynomial of degree n can have minus of g number of polynomials. So oh sorry. Yeah, I have. We have to prove that epsilon is injective. This is what it is. This is a contradiction. Okay, so here is the mess I made. Okay, sorry, extremely sorry. So let's. What I want to prove. This is not what I want to prove. Yeah, I have made a mistake here. So first I will prove. Let me write the what it is, and I will explain once again. First I have to write that if k is infinite, then epsilon is injective. This is what I have to first prove. That is, if k is infinite and epsilon f is equals to epsilon g for some fg coming from the field kx, then f has to be equals to g. This is what it is. So let's start f and g two elements for which degree n and this happens. Then we know that k is infinite. Okay, let let k be infinite, and we have two polynomial f and g of degree n1 n2, and we have ef equals to eg. And with the logicality we have assumed this, and f minus g is again a polynomial of degree n, and then we will have this one. Okay, that means we have this one. That means p has infinite number of zeros because k is infinite. But here, as k is infinite, then f minus g have infinite number of distinct zeros. But this can't happen. Okay. But this is a contradiction. This is a contradiction unless f minus g is the zero polynomial. That says f equals to g, and that says epsilon is injective, because we have started the fact that ef equals to epsilon f equals to epsilon g, and we arrived f equals to g. Okay, that's injective. On the other hand, if it is injective, then we have to prove that this is finite. So that is infinite. So let's take epsilon is, but here if I can prove that if k is finite, then epsilon cannot be injective, then that's enough, and that's what we have done here. That that's what is okay. Right now we have both sides. I have little mess with this problem, but right now it is completely clear. What is epsilon? Okay, I have not seen. Epsilon is the map. Epsilon is a map. Here it is. I have sorry. I have not noticed that comment. Epsilon. What is the epsilon? Epsilon is the map that sends. Epsilon is the map that sends. That is map from kx. Kx. What is the elements in kx? That's the polynomial. That goes to k to the power k. What are the k to the power k? That is what it is called. K to the power k. That is a set of all k valued function from k. How it is going? F going to epsilon k, that is a function from k to k. How it acts? A epsilon at a is equals to at b is equals to fb. This is what it is, the epsilon. Okay, clear what is epsilon here? Is it clear what is epsilon here and how this problem solves? Because I have let confused little bit in between class, so but right now it is correct. So let me go ahead read once again. So what is epsilon? K is a field, kx is the set of all polynomials, and k to the power k is the set of all k valued function from k, and epsilon is a map that says kx to sends every element f to ef is a map from f k to k, that's at the point b is gives fb. Now what are the zero element in polynomial? Those are the elements where all coefficients are zero. Now we have to prove that epsilon from kx to k to the power k is injective if and only if k is not finite. That means k is infinite. Okay. So let's first start with that from this side to this side, that if k is infinite, then we'll prove that epsilon is injective. What is mean by injective? If it is enough to proving that if we consider f and g two function, then epsilon f equals to epsilon g implies that f equals to g. That's what it is injectivity means. So so here f and g two polynomial with the degree n1 n2. Let's take f minus g is the polynomial which has degree n1, because I have assumed n1 is greater than or equals to n2. Then by this condition says that e epsilon of f minus g is 0. That means f minus g at the point b is equal to 0 for all b belongs to k. But we have assumed that k is infinite field. That means the polynomial f minus g have infinite number of distinct roots or zeros. But that can only happen if f minus g is the zero polynomial. That means f equals to g. That says f epsilon is injective. On the other hand, what we have to prove? That if epsilon is injective, then k is infinite. Okay, that's equivalent to proving that if k is finite, then epsilon cannot be injective. That's what it is equivalent. So that's what I'm going to prove. That if k is finite, then we have to show that k is not injective. Let's k is finite. Then we have this finite number of elements, and these are all elements in k. So let's consider a polynomial. Let us consider a polynomial x minus a1, x minus a2 all the way x minus an. So clearly p of ai is equals to 0 for all I equals to 1 to n, right? That says that says that says epsilon of p is equals to 0, right? Epsilon of p is equals to 0. But here p as an polynomial, it has non-zero coefficient, right? So that means p is not a zero polynomial. So epsilon is not injective because we have non-zero polynomial which is maps to the zero map. I hope it is clear. Now, if you have any doubt, please let me know. I know I have made little mess here, but if you have doubt, you can ask me. Or not visible because maybe there will be network issue from my side. So Okay, so there is another problem in that one itself, which is little bigger, and which I need to solve. This is that so what we obtain that epsilon is injective if and only k is not finite, right? Now we'll prove epsilon is surjective if and only k is finite. So that means if we can prove this one, let's assume the B I have proved that epsilon is surjective if and only k is finite. A set or a field cannot be finite or infinite simultaneously. That means the map epsilon cannot be bijective. That's what it is mean. That means the number of entries in the field kx is not same with the set of all k valued map from k. That's separate thing. I will come at the end. But interestingly, both are very other direction. If k is finite, you will have one fact. If k is infinite, you will have one fact. What we proved? If k is infinite, epsilon is injective. Now we'll prove if k is finite, epsilon is surjective, and that is if and only. So let's go to the problem. Let's write the problem. Epsilon, once again I am writing from the set kx to k to the power k is surjective if and only if k is finite. Okay, this is what it is. But here it is instructed to use some methods which I am writing here. I will also use those methods as a hint. This is one of the hint that you have to use this one, and this is one of the hint. I hope I'm tagging correctly. Yeah, this is hint one. Okay, we have to use this hint to solve this one first problem. And there is two more hint, but at least I will try to solve this one and one more. So what it says, this is hint one, that epsilon k is surjective if and only if its k is finite. Let's start with k is finite. Let k be finite. So then what I have to prove? Epsilon is surjective. That means for every k valued function from k to k, then we need to prove, let me write everything, then we need to prove epsilon, which is the map from kx to k to the power k, is surjective. That is, what is equivalent? That is, for any function f from k to k, there exists another function or polynomial. There exists a polynomial. There exists a polynomial p in kx such that epsilon p at the point a is equals to f of a for all a coming from the field k. This is what it is we have to prove. So we have to construct. If we are giving f, we have to construct this polynomial p. This is what it is our task under the assumption that k is finite. So as k is finite, so we can give some fixed value. So let k is equals to this set. Let k is equals to this n number of element is there. Okay. So here we have to construct. It is asking to check with this. Here it is a not to n. Okay, I will write. Okay, a not to. So let's take a not to n. This is what it is considered. A not to a1 to n. So here it is asking you to that to construct to to use this type of polynomial. That's what it is. So let bi is equals to f of ai for all I equals to 0 to n. So what we have given, we already given a function f from k to k. So whenever we have k is this set, so f of ai will some value, so that is b1, b2, bn. But note that here b1, b2, bn need not be distinct, but k, a1, a0, a1, a2, an, they are distinct because they are elements in a set. But bi can be same. For example, like f can map 1 to 1, f can map 2 to 1. Here these one are the behaving like bi, and this one to behaving like a1, a2, an. Okay. So if we have bi is equals to fi, then if we construct the polynomial look like this way, then it is saying that this will work. So how the polynomial is saying to construct? The polynomial is saying to construct the polynomial p is equals to summation of I equals to 0 to n bi. Bi is actually f of ai by ci. What is ci? I am writing ci. It's better to not writing here. So let me write that polynomial is x minus a1 all the way x minus ai minus 1, x minus ai plus 1 all the way x minus an. Achha, it will be start with x a minus 0. Yeah. Look at very carefully. This is called Lagrange's polynomial. By here, if you look at carefully, here we have missed ai. Okay, so this ai minus a1 all the way ai minus ai minus 1 and ai minus ai plus 1 all the way ai minus a. So note that as all ai's are distinct, so this is 0, this is 0, this is 0. All ai's are distinct, so these below terms, all the factors in below are non-zero. And as we have removed ai from this position also, so this is, so we have taken polynomial p as this one. So now we will be checking that epsilon p. Now we check epsilon p is equals to f. How we can check? By evaluating at each point. So epsilon p at the point ai, what it happens? That is equals to summation of I equals to 0 to 1. Let's write it as aj, right? Aj n f of this is ai. There is no problem because this ai is I is coming from this index, and it will be like aj minus a naught all the way aj minus ai minus 1 and aj minus ai plus 1 all the way aj minus an. And what is the below term? Below term is aj minus a naught all the way aj minus ai minus 1 aj minus ai plus 1 all the way aj minus an. So clearly the below term will cancel out. No, it will not cancel out always. There is a catch. You have to be very carefully. So there is a factor. If you look at carefully the factors, what are the factors? That x minus a naught, x minus a1 all the way x minus ai minus 1, x minus ai plus 1 all the way x minus an, and this is like ai minus a1. That this is where I mixed it. Yeah, that's okay. Below term is no changing. Below term is constant, right? An minus a naught, not an, ai all the way ai minus ai minus 1, ai minus ai plus 1 all the way ai minus an. We have this one. So, okay, let me write as I have written. So ai minus, this is a naught, a1 all the way ai minus ai minus 1 and ai minus ai plus 1 all the way ai minus a. We have this one. So if we replace x by aj, if you replace x by aj and j is not equals to y, what will happen? If j is not equals to y, there will always exist a factor which says x minus aj, that factor will be there, because all the factors will be in the above is there except the factor x minus ai. But if j is not ai, that factor will also be there. So that factor will make this numerator to 0. So that means if we replaced here aj, then only the jth component will survive, otherwise all the component will be 0. Okay, is it clear? Because this is what it is, the beauty of Lagrange's polynomial. So this will be f of aj, because there is what we have, there is total n plus 1 number of factor, and each of them are look like this way, right? Each of them are look like this way. But if we evaluate at the point aj, then only one factor will survive, all other factor will be 0. Why all other factor will be 0? Because in all other cases where j is not equals to I, when I is something like that, that's not equals to j, in that case you will always have a factor above of the form x minus aj. In here, if I is not equals to j, there you will have the factor x minus aj, factor will be there in somewhere. That will make that things 0. So that means only when it is j, only when I equals to j, in that case above and below term are same. If you replace x by ai, if I take j is equals to 1, sorry, j equals to I, then replacing x by aj means replacing x by ai. In that case, numerator and denominator are same, that will be cancelled out, and that will have f of ai or aj. In that case, I equals to 0. That means this is equals to f of aj, right? So that means epsilon of p, that is equals to f, as j equals to 0 to n is an arbitrary. We have started with an arbitrary things. You can check by one, but that's irrelevant. You can start it with any j and give the correct argument, that's better. Is an arbitrary, is chosen as arbitrary. So what we proved? We proved if we start any element f in k to the power k, so we proved if f is any element in k to the power k, there exists all p in what is called this is kx, such that epsilon of p is equals to f. Okay, so that says epsilon is surjective. Okay, now what we have to prove, that epsilon is this is what it is, one side is now. Now for other side, if epsilon is surjective, then we need to prove k is finite. Okay, this is what it is, we need to prove. Okay, so how one can prove this one? Okay, so just a minute. Okay, so let epsilon is positive, epsilon is surjective, but k is not finite. Okay, choose any element a from k and define a map delta a, that's called the Dirac delta function. You can say k to k, how it is, k is a field, there is a 0, right? So how it is, and 1 is also there. So delta a only at the point a is equals to 1 and delta A at the point B is equals to 0 if B is not equals to A and B is coming from the field K. Then it is what it is, right? So point is that what I have to prove is that that if I can prove that we will not have any pre-image, then we are done. Then if we can prove that epsilon does not have any pre-image for epsilon does not have any pre-image for delta A, then we will arrive at a contradiction. Then that means K can be finite. That's what it is. Okay, that's what it is. And what is mean by that? There does not exist. There does not exist any P coming from the field coming from the polynomial Kx such that epsilon P is equals to A. Sorry, delta. That's what it is. So if there is any, if there is any such polynomial, K is I have taken finite. Okay. If there is P, if there is P coming from Kx such that epsilon P is equals to delta A, then P at the point A is equals to delta A at the point A is equals to 1, and P at the point B is equals to delta A B, that is equals to 0 for all B coming from the field K and B is not equals to A. In that case we have this one, right? But we have assumed K is not finite, that is infinite, right? But what it says, the polynomial P has root except every element, but it says, but above argument says every element of K except A is 0 of P. Zero of P. That is P has infinite number of zeros. But P is a polynomial. It can have maximum finite number of zeros because P is a polynomial of any degree, right? But P is a polynomial of some degree, right? So it can have only finite number of zeros or roots. Zeros, it is zeros, finite number of zeros. That is a contradiction. Where is the contradiction? Because where is the contradiction? Because if we start the fact that epsilon is surjective, but still the field is not finite, then we can we get a polynomial which is finite degree polynomial, or we get a polynomial which has infinite number of zeros or root, but that's not possible. So that is a contradiction. So then K that is a contradiction. That thus K cannot be finite. Sorry, K cannot be infinite. K is infinite. K is finite because K not finite, there is a problem. So K is finite, there is no problem. So this is what it is. So let me go through once again what the surjectivity part says. So what the surjectivity part says, if epsilon is surjective, then we need to prove that K is finite. If it is not finite, then there exists an A such that delta A from K to K, that delta A at the point A is 1 and delta A at the point B is 0 for all B not equals to 0. But we have assumed that epsilon is surjective. That means there exists a polynomial p for which epsilon p is equal to delta a. That is a polynomial, and whenever it is polynomial, it has some finite degree, right? So, but what we'll obtain using the fact that how it is working, so we'll get that p is a polynomial which is zero at all point of the field except the point a, but k is infinite field. So that means p has zero at all points of the field k except a, but that means p has infinite number of zeros, but that's not possible. So that means our assumption that k is not infinite, that is k is not finite, that is k is infinite, that false. That means k is finite. So this is what it is. So that settles. So what we obtain? What we obtain? So observe or remark, you can say. Epsilon from kx to k to the power k given by epsilon of f. How it is working? F goes to epsilon f, that is a function from k to k, that at the point a is f of a, cannot be bijective, cannot be a bijective map, because if it is surjective, then it is infinite, finite, finite. If it is surjective, then it is finite. If it is injective, then it is infinite, and that is if and only. So it cannot be a bijective map. Okay, so I have very less time. Till that, if you have any doubt, please let me know. Otherwise, I'll try to solve very simple one questions and we will close today's session. But let me find one simple questions. But till that time, if you have any doubt, please let me know. If you have any doubt, please let me know. Otherwise, I'll solve a very quick problem. Okay, so let me check one by one. Just a minute. Okay, I think it's better to. I should have written the. Okay, I will write the problem. Okay, so what's the problem? Yeah, so this is one of the questions. So let me do it quickly. So till that, if you have any doubt, please let me know. I will try to solve that first, and then if if I get time, then I'll come here. So what is that? Let V is equals to R4. That is the tuple of four elements, and they are over the field R. Be a vector space over R. We know. Then let's say the question is which of the following is the subspace of W? Which of the following is a subspace of V. So first option, set of all vectors of the form W, X, Y, Z, where W plus X plus Y plus Z is equals to 2. Option B, set of all vectors of the form W, X, Y, Z, where W, X, Y, Z all are positive, all are greater than 0. C, set, you can check simultaneously whatever option I'm giving. Set of all vectors of the form W, X, Y, Z, where W plus X plus Y plus Z equals to 0. So this will be the correct answer. I'll check, but other will be automatically fail. Set of all vectors of the form Z, where W square plus X square plus Y square minus Z square is equals to 0. So this is the question. Quickly, this is the answer. I'm going to say this very quickly. So first of all, why this is not 0, not true? That why this is not true? Because 0, 0, 0, this is the element which is not in the, not belong to the set. If I take W is this one, that collection of all these for which this happens, this is not in W. If I take W be the set of all these for which this positive, then inverse does not exist. Additive inverse does not exist. So that's why it is also not true. Additive inverse does not exist, because if it is subspace means it itself is a vector space, right? So that means if we have an element that should have that will be the group with respect to the abelian group with respect to the addition. When it is becoming an abelian group, that means it must have an additive inverse. So additive inverse of group, something like if you take 2, 3, 4, 5, what is the additive inverse? That is -2, -3, -4, -5, right? But here it is saying the elements will look like that if we all are positive. So that means if we consider like 1, 0, 0, this is satisfying all the condition. And what is the additive inverse of this? That is -1, 0, 0, but this does not belongs to W. Okay. So that means additive inverse does not exist. So that's why this is not true. Why this is not true? This is, you can create a counter example. So for example, if you take 1, 0, 0, 0, this is okay. So basically, what are the element here? What are the element? You can't take just absurdly. So you can look at carefully 1, 1, 0, 0, 1. This is and 1, 0, 0, -1. This both the element are in W. W is the set of all this. Then, but if you take their addition, what is the addition? That is, if you add them, then what 1, 0, 1 plus 1, 0, 0, -1. What is that? That is equals to 2, 0, 0, 0. But let's check whether this element is there or not. If you replace W is 2 and all other element is 0, what will be 4? 4 is not 0. So that element is not in W. So this element is not there. And why this is happening? So you can take any element x1, y1, z1, w1. I think we have to take the other way, but okay. w1, x1, y1, and z1. And if you take w2, x2, y2, z2, two element in W, the set of all w, x, y, z for which this equality holds, and C as an scalar coming from the field that is equals to R, then you can easily check C of W1 plus x1, y1, z1 plus w2, x2, y2, z2. This will be C of w1 plus w2, C of x1 plus x2, C of y1 plus y2, C of z1 plus z2. This is, and you can check this is in W. You can check that this similar type of problem. So W is so this is a subspace. I hope it is clear. So if you have any doubt, please let me know. Otherwise, I will stop here. I will not do any more problem. If you have any doubt, please let me know. Otherwise, I will stop the live tutorial session in next 2 minutes if you don't ask anything. And if you don't have anything to ask, you can leave as your convenience.